Uh, Good afternoon to all. Welcome to the fourth week problem solving session for the NPTEL course, Convective Heat Transfer. My name is Ananthakrishnan. I'm a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. Before wasting much time, we can go to the topics for today's presentation and the session. So the main contents of this week's lectures are hydrodynamically fully developed flow, mean temperature in the fully developed flow. And the uniform heat flux and uniform wall temperature boundary condition, tubes surrounded by isothermal flow. So, so we'll see a few derivations, numerical type problems, and a multiple choice questions based on this week's lectures. So without wasting much time, we can move to the problems. Look into the problem. It's a question on Hagen Poiseuille flow. It's a fully developed flow through a duct, a circular duct, or it can be any duct. Determine the velocity distribution corresponding to fully developed Hagen Poiseuille flow through the annular space formed between two concentric tubes. So this case is the annular tube, that is two concentric circles over one over the another, start one over the another, and the middle space between the two concentric circles will be hollow. Let Ri and Ro be the inner and outer radii respectively. Show that the inner wall shear stress tau Wri differs from the value along the outer wall tau Wro. Calculate the friction factor for this flow by using the average tau W, that is the shear stress value defined based on a force balance of type pi r outer squared minus Ri inner squared into delta P, that is pressure into area is equal to force is equal to shear stress average multiplied by the surface area, total surface area of contact. So this could be represented in this form of this. There are two parts to the question. First of all, we have to show that the inner wall shear stress differs from the value along the outer wall, and we need to calculate the friction factor for this flow by using the average shear stress value. Looking at the problem, I'll also try to solve it within another couple of minutes. So it's a derivation kind of problem. First of all, try to draw a schematic and identify what exactly is need to be solved in this kind of a problem. So I'll try to solve the problem. So this is a case of an annular tube. That means that two hollow tubes start over one another with a common center, common origin. So the outer radius is RO, the inner radius is RI, and the flow and this extends into the plane of the paper. So in this one, the flow happens through the annular space between the two concentric tubes. And let this be the x direction, and this will be the r direction. And the flow happens in the r direction. So the velocity variation will be in the r direction, because this is a fully developed flow, and we could assume that the variation of the velocity, u velocity, that is x direction velocity is u. The variation of u with respect to x is equal to 0, since it's a fully developed boundary condition, a fully developed flow condition. So we can tackle this problem by using the governing equations. We can write the governing equation in the cylindrical coordinate format, and there will be two particular terms on the convective side and one pressure term. So it's a Haken-Poiseuille flow. And here the I beg your pardon, not the convective term, but the friction term, the viscosity term. So there will be two terms on the friction side and one term corresponding to the pressure. So the pressure force will be balancing the viscosity force in the case of Haken-Poiseuille flow. Here the flow occurs in the annular space. The flow happens between the annular space between Ri and Ro, where Ri is less than any radius less than Ro. So the X momentum equation could be written as dou squared U divided by dou R squared plus 1 by R dou U by dou R equal to 1 by mu dou P by dou X. This can be written in a more concise manner, taking these two terms inside the dou U by dou R bracket. So that will be 1 by R dou by dou R dou U by dou R is equal to 1 by mu dou P by dou X. So that is the X momentum equation. In terms of the radial, the cylindrical coordinate. Now, we can, since it's a straightforward problem, we can actually give the boundary condition and then solve it to obtain the value of the velocity, the variation of the velocity with respect to the radius. So we will try to integrate it. The boundary conditions are U equal to 0 at R equal to Ri, U equal to 0 at R is equal to R outer. That is a no slip boundary condition. Inside at inside and outside one. Uh, Integrating the governing equation, and you can get a general solution. U R is equal to R squared divided by 4 mu. This is dP by dx. dP by dx, because the other direction pressure difference is neglected, ln of R plus C2. Hence, we could write C1 is equal to minus of 1 by 4 mu dP by dx R outer squared minus R inner squared divided by ln of R outer divided by R inner. Similarly, C2 is equal to minus of R outer squared divided by 4 mu dP by dx minus of C1 ln of R0. These are the constants by applying the boundary conditions onto this general equation. Applying boundary conditions to the integrated form. And substituting these values. So we'll get C1 in this form, and substituting C1 in this C2, we'll get the value of C2 as well. Then back substituting, we'll get the value of U. Then we'll do some algebraic manipulations to this equation, and then we can represent the equation in a much better manner. So in this particular case, what we are asked to find is that inner wall shear stress and the outer wall shear stress are different. So we have to calculate the value of the inner and the outer wall shear stress. And the second part of the problem, we need to calculate the friction factor for this flow by using average shear stress based on the pressure shear stress balance for a control volume. And for that, actually, we require the value of the average shear stress and the value of the shear stress at the inside and the outside walls. So the average value of the friction factor depends upon depends upon the shear stress as well as the average velocity, the mean velocity value. So in this particular equation, we need to find the value of the mean velocity straight away. So what we could write, the mean velocity, we can represent it by U, capital U. So what you could write is that U into the area, cross-sectional area, P R outer squared minus R inner squared is equal to integral of 0 to 2 pi in the theta direction and R inner to R outer variation with respect to radius is equal to the local variation of the velocity UR R d theta into dr. So this could be represented as if you take a normal. So assume this to be the center and this to be a local control volume. So the variation, the area for the flow, you can assume the flow happens perpendicular to this area, cross-sectional area. So U into the area will give the volume flow rate, the mean volume flow rate. Assuming the density remains a constant, you can assume U into pi R outer squared minus inner squared is equal to integral of this particular term. So this area you could represent it by the variation in this direction is equal to dr, and you can assume this to be a square, and the dr is very small such that this section will be equal to this section equal to r d theta. So the inner radius is r, and this direction, the variation with respect to theta is d theta. So the width dimension of this control volume is r d theta. We assume that this length is very small, so that this section will be equal to this section. So therefore, the area through which the flow happens is r into d theta, r d theta into dr. So same multiplied by the velocity local velocity. So this integration will give us the mean velocity value. And performing simplification, we'll get the result. The mean velocity U is equal to R outer squared by 8 mu into dp by dx 1 plus Ri by Ro the whole squared plus 1 minus Ri by Ro the whole squared divided by ln of Ri divided by Ro. This will be the value of the average velocity or the mean velocity term. So you can denote it by the equation 3. So this is one particular important factor because the shear stress, in order to calculate the friction factor, you require this average velocity term. If it was a flow over the flat plate, you could have directly taken the free stream velocity. Since this is a flow in a tube or an annulus, you have to take the mean velocity term in order to calculate the friction factor. So now we have obtained the value. The next part is that we have to calculate we have to show that the inside shear stress will on the shear stress on the inside wall at radius Ri will be different from the shear stress at the outside wall at radius r equal to r outer. So, so we know the value of the velocity. The velocity is given by the equation 2. UR is equal to r squared by 4 mu dou p by dou x C1 ln of r plus C2. So what we do is that we differentiate in order to calculate the shear stress at the inside wall, first part of the question. At the inside wall, dou I is equal to mu into dou u by dou r at r is equal to ri. So differentiating the velocity equation, it will be equal to, you could write it in terms of uh, ri by 2 dou dp by dx plus mu c1 divided by ri. So c1 is this constant. Similarly, the shear stress at the outside wall, so to you differentiate the velocity, the equation that you have obtained with respect to r, and substitute r is equal to r outer dou u by dou r at r is equal to r outer, will get minus of r0 by 2 dp by dx minus of mu c1 divided by ri. So from this, it's clear that even without substituting the C1 value, it's clear that the value of tau 1 is not equal to tau 2. That is, shear stress will be different at the inside as well as and outside walls. Now coming to the second part of the problem, the question asks that we have to calculate the friction factor by using the average shear stress value, and we could use this kind of a force balance equation to obtain this. So it's given that tau average into 2 pi into r outer plus r inner L is equal to this particular form. This is shear stress average into total surface area at the inside and the outside part. So this is the form of shear stress average. So if you substitute the value of the shear stresses at the inside and outside, outside the wall surfaces, and then we can try to obtain the average value of the shear stress, and then we can calculate the frictional factor, friction factor in terms of the average shear stress value as well as the dynamic pressure in terms of mean velocity. First of all, second part, we can write average shear stress so average into the total perimeter 2 pi 2 pi into r outer plus r inner, so average into 2 pi into r outer plus r inner is equal to the inner shear stress multiplied by 2. So the L term will also be there in inner 2 pi r inner plus L multiplied outer shear stress into 2 pi r outer and the L. So L get cancelled. Substitute the value of the inner and the outer shear stresses that we have obtained in the first equation, these two tau value. Then substitute in the value of tau I and tau outer. You get tau average is equal to minus of half dp by dx into r outer minus r inner. Therefore, the friction factor F is equal to tau average divided by half rho u squared. So the tau average, we substitute the value then of minus of half dou p by dou x into r outer minus r inner. But even then, the velocity factors, you have to substitute the value of the mean velocity in this equation. So we have obtained the value of the mean velocity. We can make some kind of a simplification to this formula. You just separate the u into two terms, right? This half into rho u as 2 by rho u, and then you can write this as tau average divided by u. Making some simplifications and substituting the value of tau average and u in this one, u will be equal to a r0 squared divided by 8 mu dou p by dou x into 1 plus ri by r outer squared plus 1 minus of ri by r outer squared divided by ln of ri divided by ro. So the only thing that differentiates between these two, there is a dou p by dou x for the tau average terms as there is a tau the dp by dx term for tau average as well. We substitute it straight away to the other equation. So this will be equal to 2 by rho u. So this particular term you have to somehow manage in the form of the hydraulic diameter. So if you multiply and divide the hydraulic diameter on the top and bottom side, you can and put mu as well onto the left hand side. We will be able to write this in the form of the Reynolds number. So it's doing a bit of mathematical manipulation. So you can write it in this form, and then you can write mu divided by mu. And then tau average, you substitute the value. Substitute the value of this minus of half dp by dx into r outer divided by r inner divided by u average value is equal to r0 squared by 8 mu r0 squared divided by 8 mu into dou p by dou x dp by dx dp by dx multiplied by 1 plus ri by r outer squared, the constant term, 1 plus ri by r outer the whole square plus 1 minus of ri by ri, 1 minus of ri divided by r outer squared divided by ln of ri by r0, ln of ri by r0. So this actually gives the value of the friction factor, but we have to do some kind of simplification. This doesn't look straight away good. So dp by dx will get cancelled out. This mu and mu gets cancelled out. The dh you can take it outside. Then you can represent this as rho u dh divided by mu. That is the Reynolds number part. this 2 will get cancelled out. In the end, there will be a lot of terms that will be remaining. The hydraulic diameter will be equal to 4 into area divided by 4 into cross-sectional area divided by perimeter. So in the case of an annular tube, the cross-sectional area will be equal to pi into r outer squared minus r inner squared divided by the perimeter will be total perimeter. So that will be equal to 2 pi into r outer plus r inner. So we can simplify this 2 pi. R outer square minus R inner square can be written as R outer plus R inner multiplied by R outer minus R inner. So only R outer minus R inner remains. So there is this R outer minus inner. There is another term of R outer minus R inner on the top as well. So these get multiplied with each other. So we can simplify this friction factor F is equal to 16 divided by a Reynolds number for the hydraulic diameter DH multiplied by 1 minus of Ri by R outer is 1 taking the R outer outside can be written as Ri by R outer the whole square. The two Ro minus Ri terms are there. So taking Ro out from both of them, you get Ro out squared, and that will get cancelled out with the R out squared that is remaining outside in the denominator. And the denominator will be kind of same. It will be having this particular term 1 plus Ri by Ro squared 1 plus Ri by Ro squared plus 1 minus Ri by Ro squared divided by ln of Ri divided by R outer. So this is the friction factor. This is the value of the friction factor that can be obtained from the direct force balance of a control volume that equates between the pressure and the cross-sectional area as well as the shear stress into the surface area. So in terms of average shear stress, we could represent everything in the form of this equation. So this is a friction factor corresponding to an annular tube. So we have solved the two problems in this case. First of all, we have shown that the inner and the outer shear stresses are different. For that, you have use of first principles. Calculate mu in dou u by dou r. For that, you require the value of the velocity at the variation of the velocity with respect to the radius. Based on that, you have calculated and shown that the values of shear stress at the inner and outside walls will be different at different radiuses. Inner and outer radiuses will be different. Then the second part is that using this average shear stress, we have to determine the value of the friction factor. So the average shear stress can be represented in terms of the individual shear stresses at the inside and the outside radius and the walls. And then correspondingly, that can be written, that can be the various values of the average velocities or the mean velocities can be substituted, and you can get the friction factor corresponding to the annular tubes. So one corollary we can add to this problem is that in the case of a circular tube, in the case of circular tube, the Ri tend to 0. In that case, substituting this, the this particular fraction will reduce it to this particular fraction will be limited to 1. So in that case, when Ri will become equal to 0, the denominator will become equal to ln of 0, and it's a negative minus infinity term. And then 1 by minus infinity term will be equal to 0. So that on the whole denominator only 1 remains. On the numerator also 1 remains, and the friction factor reduces to 16 by Reynolds number, which is the normal equation that is for the finding friction factor. through the round tube. So this is one way to cross verify whether this equation that we have obtained for the annular tubes is right or not, because it reduces to the normal circular tube case when we put Ri is equal to 0. So that completes our first problem. This was a problem to determine that the inner and outer wall shear stresses are different, and then to calculate the friction factor based on average shear stress parameter. Now you can move to the second problem. Okay, this is the case of a uniform heat flux. That we can assume that the heat flux through the walls of the channel of this figure is uniform. The flow regime is laminar. The velocity and the temperature profiles are fully developed. The hydrodynamically and thermally fully developed flow. We have to derive the expression for fully developed temperature profile and show that the Nusselt number based on the hydraulic diameter is Nusselt number is equal to 8.235. Try to solve it, and I'll also try to solve it within a couple of minutes. Okay, we can see the solution to the problem. We need to prove that the Nusselt number is equal to a constant 8.235. So for a fully developed flow and heat transfer in a parallel plate channel, we should try to solve the energy equation. So the simplified energy equation will be U dot T by dou X, the diffusion term. I beg your pardon. So the U dot T by dou X, the convective heat transfer term will be equal to the diffusion term, dou square T divided by dou Y. So this is something that we have obtained from the by removing the other terms. The This is convective heat transfer term. This is the diffusive heat transfer term in the y direction. So if you assume this as the x direction, this will be the y direction. So what you could see is that the way, even though if it is a hydrodynamic flow, you could have checked that dou E by dou X will be equal to 0 for fully developed condition. It is not the same for temperature. Dou T by dou X will be varying, but the dimensionless temperature value, the dimensionless variation of the temperature dou theta by dou X, that will be equal to 0 for the fully developed flow, not the dou T by dou X. Sorry. So here the U can be written as from the tutorials as well as from the lectures uploaded. U for a hydrodynamic fully developed flow between the parallel plates can be written as U equal to 3 by 2 into U average into 1 minus of Y by D by 2 the whole squared. So this is for the case of a parallel plate by using the X momentum equation, and where we try to equate the pressure difference in terms of the viscosity terms. So you will arrive at this velocity profile. It's parabolic in nature. Now, what you could say is that this is a constant heat flux case, uniform wall heat flux case. In that case, Q bar is a constant. It is uniform heat flux case. So what you could write is that for the constant heat flux dou T by dou X, the variation in the temperature will be same as that of the mean value, variation in the mean temperature dou T by dou X. That will be equal to 2 heat flux divided by rho Cp d into average velocity. So this is the equation from the normal energy balance. We could write T0 by the wall temperature minus of in order to non-dimensionalize the temperature, we can write T0 the wall temperature. This is the wall temperature and this normal temperature at the point x comma y T0 x divided by T0 x minus the mean temperature at the x will be equal to a dimensionless temperature profile. So this is depend upon the term y divided by This is depend upon y divided by d by 2. Phi of d by 2. This is dimensionalizing. The process is called non-dimensionalizing the temperature. So we know the temperature and the denominator. What we could say is that the T0 Tx minus Tm by Tx is equal to delta T. Since we could write the heat flux in terms of Q is equal to K into dou T by dou X. What we could write is that since Q double dash is a constant, delta T divided by delta Y, that is delta T divided by R, that can be a constant. So that's why we could write delta T is equal to T0, the wall temperature at a particular point X, minus mean temperature at a particular point X is a constant. So what we could write is that the denominator term is a constant. So that gives the T0 X, the numerator is equal to a constant multiplied by this particular right hand side term. Now what we do is that we substitute the equation 2, 3, 4, and 5. Substitute equation 2, 3, 4, and 5 in 1. So in that case, we can reduce this particular equation into a non-dimensional form. But before that, x and y needs to be non-dimensionalized as well. So what we could write is that the dou t by dou x could be written in terms of the most important parameters in terms of delta t, and the acceleration variation will be as such x, because once you get the dou t by dou x, that can be assumed to be dou t equal to dou t m by dou x, and straight away you can write it in terms of the heat flux. So this particular term is kind of a constant, and when you substitute, you can write it in the form of the average velocity term. So this left hand side term is kind of straightforward, but it's a right hand side term, that is the variation with respect to y, that matters most. So y has to be non-dimensionalized. How we non-dimensionalize is that we'll put eta is equal to y divided by d by 2. So phi can be written in the form of eta. No, phi of eta, this phi by d by 2 can be non-dimensionalized as eta. So write it as 6. So 5 and 6 in 1. So substituting all these parameters, what you could write, the y momentum equation will be equal to, sorry, the x momentum equation will be equal to 3 by 8 q double dash divided by delta t 2d divided by k into 1 minus eta squared equal to minus of dou squared phi divided by dou eta squared. So basically what we do is that dou phi by dou t by dou y you represent in the form of dou t by dou phi by dou eta. That could be represented as dou t by dou y can be written as dou t by dou theta, then dou theta by dou eta by dou y. So substituting these three into this, we could write dou t by dou y in terms of dou theta by dou eta. And then again resubstituting it in for one more differentiation, we'll get in form of dou square phi by dou eta square, taking the constant terms onto the left hand side and substituting dou t by dou x in the form of 2q double dash divided by rho cp dou u. We can arrive at the equation where the only term, the additional terms will be these particular constant terms. So I can denote it by 7. Here it is a it's a parallel tube. So hydraulic diameter will be equal to 4 into area divided by perimeter. So that will be equal to 2 times the width of the parallel channel. So that will be equal to hydraulic diameter is equal to 2 times the width, and we could write Nusselt number is equal to the heat flux into hydraulic diameter dH divided by K into delta T. So this is basically how we'll get is that Nusselt number is equal to H into hydraulic diameter divided by H into characteristic length divided by K, where could be written, characteristic length will be equal to the hydraulic diameter, and H could be written as heat flux heat flux divided by the temperature difference. That is T of wall minus of T mean temperature. And we can substitute it, and then in this particular equation, and then again integrate, substituting and integrating. Substituting and integrating, we can write it in terms of Nusselt number, eta, and a constant C1 equal to minus d5 divided by d eta. So you require one more boundary condition. You require a boundary condition to get the value of C1. So what we could write is that in order to calculate the C1, the variation of the heat flux with respect to eta, the variation of the non-dimensional temperature with respect to eta, that value will be equal to 0 at eta is equal to 0. Basically, at a point y equal to 0, the temperature profile with respect to y will be equal to 0. Maybe we could assume that it is a parabolic profile at the center line when y is equal to 0. This is y, this is plus y by 2, and this is plus d by 2, and this is minus d by 2. So at y is equal to 0, eta is equal to 0, and you could write it as dou t by dou y equal to 0. And this can be written as dou phi by dou eta equal to 0. So boundary condition says that at y is equal to 0, dou t by dou y is equal to 0. Invoking the same boundary condition as that of far away from the wall, nearby the boundary line in the case of a flat plate, where dou t by dou y will be equal to 0. The same boundary condition due to the symmetry condition at dou t by dou y will be equal to 0 at the center point at y is equal to 0. So in this case, it could be written as dou phi by dou eta is equal to 0 at eta equal to 0. Substituting that, we'll get the value. Substituting, we'll get the value of C1. You can write it as 8. C1 is equal to 0. When you substitute right hand side is equal to 0 and left hand side is equal to 0, you'll get C1 is equal to 0. So you can write it straight away. Then we can integrate it once again. So you get phi is equal to 3 by 16. Nusselt number, a constant C2 eta squared plus 1 by 6 eta raised to 4. So we'll get the form dimensionless temperature in terms of eta. Then the next step we need to so in this particular problem we have to determine the value of Nusselt number. For that we need to get the value of Nu. So in this case we have phi that is the temperature. So that is dependent upon the wall temperature and the uh, temperature at one particular point divided by the value of divided by the delta T value that is dependent upon the wall temperature and the mean temperature at one particular point. And we can substitute the value of eta as well. Then finally, we need to get the value of Nusselt number. Before that we need to find the value of C2. We invoke another boundary condition. We can write at y is equal to plus or minus d by 2, t is equal to t0. That implies that at eta is equal to 1 or plus or minus 1, phi is equal to 0. Substituting this, substituting eta is equal to 1, we can write it as, and phi is equal to 0. We'll get the value of theta. We'll get theta is equal to 5 by 6. You just substitute plus or minus 1, it doesn't matter because the power is in the even term. So we can straight away get it as C2 is equal to 5 by 6 for both these roots. Substituting, we'll get the value of this equation will reduce to 3 by 8 Nusselt number eta minus 1 by 3 eta cube plus 5 by 6 is equal to minus of dou phi by dou eta. So that is very straightforward. Now what we have to determine is we have to determine the value of Nusselt number. So that requires a bit of ingenuity. We have to actually determine the Nusselt number such that the condition of the mean temperature holds true. So we till now haven't used a mean temperature equation. So what we could write is that mean temperature. Till now we have used a term for mean temperature, but we haven't used the mean temperature equation as such. So what we could write is that T0 mean temperature calculation T0 minus Tm into U into D is equal to minus of integration minus P by 2 to D by 2 U into T outer minus T into dy. So now we can substitute equation 2 of the, this is in terms of U. You can write it in terms of average velocity as well as a dimensionless parameter and the non-dimensional temperature in terms of T0 minus T, delta T into 5. And one more thing, we could use the final value of the phi as well. So phi also you have got in terms of eta and then Nusselt number. So beg your pardon, there was a small correction. Beg your pardon, there was a small correction in this equation. So this substitute in this, we get the value of 5. This okay, pardon, there's a small correction. So so the phi is equal to 3 by 16 Nusselt number 3 by 16 Nusselt number into 5 by 6 minus eta square plus 1 by 6 eta raised to 4. So you need to correct it accordingly. So mean temperature is equal to T0 minus Tm into UD. So this you can get from the equation number 2. This you can get from equation number 5 in terms of delta T, in terms of 4 and 5. 4 and 5. And finally, 5 in terms of equation 10. 5 in terms of equation 10. We substitute the values and then try to minimize it. We'll get, and then integrating with respect to minus d by 2 dy, you'll get a concise form that left hand side 1 is equal to 9 by 32 Nusselt number integral of minus d by 2 to d by 2 could be written in terms of non-dimensional term, that is 2 times of 0 to 1 into 1 minus of eta squared. This eta squared actually comes from, a part of it comes from this equation u, y minus d by 2 is equal to 1 minus of eta squared, and uh, and 5 by 6 minus eta square plus 1 by 6 eta raised to 4 comes from 10th equation, substituting 5 in terms of Nusselt number this term, taking the Nusselt number outside and integrating, we'll get Nusselt number is equal to 140 divided by 17 equal to 8.235. So basically what we did was that we had a energy equation. We already found the value of the mean velocity in terms of the local velocity, and we try to use a non-dimensional approach in this case, because in the case of temperature varies in x direction, but the non-dimensional temperature doesn't vary. And in the case of constant heat flux, we also know that the temperature variation of the x dou T by dou x will be same as that of the mean temperature variation dou Tm by dou x, which itself will be same as that of the whole temperature variation dou T0 by dou x. So using these three values, we can actually find the non-dimensional temperature phi, that is represented by equation 9. And then you can use the mean temperature equation, and thereby from that you can finally get the value of the Nusselt number in terms of as a constant for a parallel plate, 8.235. So this is a straightforward problem, but it requires the hydrodynamically fully developed velocity profile in terms of velocity as well. So for that, this is a prior requisite. That solves the second problem. Now we can look into the third problem. It's a numerical problem. Just look into it, and I'll also try to solve it in a couple of minutes. Okay, we can look into the third problem. A water stream is heated in fully developed flow through a pipe with uniform uh, heat flux at the wall. The mass flow rate is m dot is equal to 10 gram per second. The heat flux Q double dash is equal to 0.1 watt per centimeter squared. And the pipe radius R0 is 1 centimeter. The properties of water are the dynamic viscosity is 0.01 gram per centimeter second. Thermal conductivity is 0.006 watt per centimeter Kelvin. Calculate the Reynolds number based on the pipe diameter and mean fluid velocity. The second, the heat transfer coefficient. The third, the difference between the wall temperature and the bulk mean fluid temperature. So we'll try to draw the schematic straight away. So it is T0, mass flow rate, mean temperature, heat flux is a constant, and the diameter. So given values straight away in the question, we have to calculate the first of all the Reynolds number. The Reynolds number RE is equal to rho UD divided by mu. Then we have to do some kind of a simplification or to arrive, since the mass flow rate is given in the problem, we have to do some kind of simplification to arrive at the Reynolds number term from the mass flow rate. So we know that mass flow rate is equal to rho into velocity into the cross-sectional area. So from this we can calculate the rho u is equal to m dot divided by pi t raised to 4 divided by 4. That will be equal to m dot will be equal to 10 gram per second. Diameter d will be equal to 2 centimeters. So we'll get it as 3.18 gram per centimeter squared second. Therefore, substituting this value, Reynolds number is equal to 3.18 gram per centimeter squared second multiplied by diameter is 2 centimeter divided by the value of the dynamic viscosity is 0.01 gram per centimeter second. So cancelling out all this parameter, you get the Reynolds number value equal to 637. So this confirms that the flow through the pipe is laminar. If it is less than the transition Reynolds number 2300, you can assume this to be laminar. The second part of the problem, we have to determine the heat transfer coefficient. So since this is a laminar flow and the flow is fully developed through a pipe, we can assume Nusselt number is a constant, and it's a constant wall heat flux case. So as was mentioned in the lecture, like through the detailed solving of the heat transfer coefficients, through the detailed solving of the temperature variation, the gradients of the temperature in the x direction, we assume that the few of them are same. So the mean temperature gradient will be same as that of the normal temperature gradient, will be same as that of wall temperature gradient for uniform wall heat flux. And just like the previous case where we have solved for the parallel plate, you can solve it for the circular tube as well, and you will get a constant value of Nusselt number that is equal to 4.364. For uniform wall heat flux, case, we can use a constant Nusselt number 4.364 that follows the same approach as that of the second question. Then we have to determine the value of the temperature difference between the wall as well as the mean temperature. So we could write the heat flux is equal to heat transfer coefficient multiplied by the temperature difference between the wall and the mean temperature. So that will be equal to this H can could be written as Nusselt number uh, into K divided by the hydraulic diameter or the diameter of the tube. So Nusselt number is equal to 4.364 multiplied by K is equal to 0.006 watt per centimeter Kelvin divided by diameter is 2 centimeter. Uh, and then heat flux will be equal to given in the problem 0.1 watt per centimeter squared. So this will be equal to 0.1 watt per. Therefore, T0 minus Tm is equal to 7.64 Kelvin. That will be the temperature difference between the wall as well as the mean temperature of the bulk fluid. So that solves the problem. It was a straightforward problem that takes into account the energy balance between the heat flux that is incoming to the fluid as well as the heat that will be transferred based on the convection part. So rather than going into the equations or the temperature profile straight away, we can use those equations that have been derived from the lectures. Since it's a case of a uniform wall heat flux and laminar flow, hydrodynamically fully developed, thermally fully developed, we could assume that the Nusselt number is a constant. We follow the same approach as that of the parallel plate in the previous case. We can get the value of the Nusselt number is a constant as 4.36. And based on that, we can solve for the other parameters. So this is a we first establish that the flow is laminar. For that, we require the Reynolds number, and we find that the noise is well within the range of the transition Reynolds number. Look into the fourth problem. This question says that a water chiller passes a stream of 0.1 kilogram per second through a pipe immersed in a bath containing a mixture of crushed ice and water. Thus, the pipe wall temperature may be assumed to be T wall is equal to 0 degrees Celsius. Zero degrees Celsius. The original inlet temperature of the stream is T inlet is equal to 40 degrees Celsius. Uh, Sorry for the brief interruption. The temperature of the stream is given as 40 degrees Celsius and the specific heat is given as 4.18. If the effectiveness of this heat exchanger is 0.85, calculate the final temperature of the water stream. Under the same condition, what is the overall heat transfer rate between the stream and ice water bath? Assume that the pipe length is L, the diameter D, and the flow regime fully developed laminar. If a new pipe is to be used, D1 is equal to D by 2 and the effectiveness to remain unchanged, what should be the length of the new pipe to facilitate the same heat transfer? So we can try to tackle the problem. So effectiveness, first of all, we do not know what is meant by effectiveness, and we start from that particular point. Solution can define the effectiveness as the actual heat transfer to maximum heat transfer that is possible for the minimum capacity fluid. So in this case, water chiller passes through a stream. Water chiller passes a stream of 0.1 kilogram per second, immersed in a water bath containing mixture of crushed ice and water. The pipe wall temperature may be assumed to be wall temperature equal to 0 degrees Celsius. Original temperature of the stream is 40 degrees Celsius. We have to calculate the outlet temperature of the water stream. So since it is dipped in a huge water bath, you can assume that the minimum capacity fluid will be the flow that happens through the that flows through the tube, because the outside is a mixture of crushed to ice and water. So there the temperature difference will be 0 and the capacity will be infinity. So the minimum capacity fluid will be the flow that is happening through the tube. So the actual heat transfer, that will be MCP into T1 minus 2, T2 will be divided by the maximum heat transfer that is possible, T1 minus of T crushed to water temperature. So this TW, from this we can get the value of the T2, the first. Therefore, T2 is equal to effectiveness into T1 minus T chilled water uh, um, T1 minus of T2. So T1 is equal to 40 minus 0.85 multiplied by 40 minus 0. That is 40 minus 0.85 into 40, that is equal to 34. That is equal to 6 degrees Celsius. That will be the outlet temperature. Outlet temperature of water. The second, and the same condition, what is overall heat transfer rate between the stream and the ice water bath? So treating it as a control volume. So initially it is coming at 40 degrees Celsius, going outside with 6 degrees Celsius. We have to calculate the energy transferred by the fluid. That is equal to, we have to calculate the heat transfer rate. We do not know whether this is a constant wall heat flux or the case of a uniform wall temperature. So, but the case is that it's mentioned in the problem that the temperature of the wall is assumed to be at 0 degrees Celsius. So we can take it. We can take it straight away at 0 degrees Celsius, and based on that we can calculate the heat transfer rate that is happening between the stream and the ice water bath. So that will be same as that of the change in the heat transfer that is experienced by the flow through this tube. So that is equal to Q is equal to MCP into dt. So mass flow rate of the fluid is 0.1 into 4.182 multiplied by changing the temperature from 40 minus 6, that is 34 degrees Celsius. 3.4 into 4.182, that will be the heat transfer rate that is expected. That is equal to 14.22 kilowatt. So this neglects enthalpy change that is associated with the pressure drop through due to the fluid, due to pressure drop due to the flow for the incompressible fluids. So this is only taking into account the enthalpy change that will happen due to the temperature difference. So heat transfer rate will be equal to mCp dt. And the third part of the problem, we have to see open pressure. Here it is T mole is equal to 0 degrees Celsius. Then assume that the pipe length is L and the diameter is D. So original pipe's length is L and the diameter D, and the flow is fully developed laminar. If a new pipe of a smaller diameter D by 2 and the same effectiveness is used, what should be the length of the new pipe to give the same heat transfer rate? So Q1 is equal to Q2, but the only difference is that it's a fully developed laminar case, so that will be equal to the heat transferred in the first case will be same as the second case. The first case will be diameter D, length L. Second case, diameter will be D by 2 and the length will be L1. We need to calculate L1 is equal to L2 and the effectiveness 1 is equal to effectiveness 2. So basically that means that effectiveness 1 equal to effectiveness 2. That means that the temperature at the outlet T2 will be same as T2 dash. So that will give heat transfer rate will be equal to heat transfer in the first case will be equal to heat transfer is equal to mCp into T1 minus T2. So the T2 will remain the same in both the cases. That gives the heat transfer will be same in both the cases as well. So we need to calculate the value of the new length as well. So how will we calculate the new length? We need to determine the new temperatures and the length that is associated in this picture. So in this case, we could see that Q1 is equal to Q2. Q can be written as if you assume that dq is more miniature section, the heat transfer across the wall dq is equal to heat transfer coefficient into diameter pi into diameter perimeter multiplied by the length of the section, that is dx temperature between the fluid, mean temperature between the fluid and the wall. So that will be equal to m dot c into dt. That is a change in temperature of the fluid. So using this, we can actually integrate it both of them. So we'll get temperature T of x. This can be written as T of x is T of x minus T vol is equal to T1 minus T vol at T is equal to at a T of x equal to 0, that is equal to T1. Similarly, T of x equal to 2, it can be written in terms of T2 as well. So this is T1 minus TW applying a boundary condition. at t is equal to t at x equal to 0 is equal to t1, it's held a constant. Based on that, you get in terms of an exponential profile x minus of h d h pi dx divided by m dot c. So we'll get it in the form of this equation. So you can represent it by 1. Similarly, the temperature at the exit point, so T2 will be equal to T wall plus T1 minus T wall into e raised to minus of h by dl m dot c at x equal to l, t is equal to T2. So based on this, we can write the effectiveness as in terms of T minus, the effectiveness will be written as T the T2 minus TW divided by T1 minus TW is equal to e raised to minus of h by dl. So if so, the effectiveness is equal to T1 minus T2 divided by T1 minus T volt. T1 minus T2 divided by T1 minus T volt. So here we know T2 minus T volt. So taking a 1 minus of this one, so we know T2 minus T volt divided by T1 minus volt is equal to this term. So taking a 1 minus 1 at the left hand side, there we get in the form of T1 minus T2 divided by T1 minus T volt, that is equal to 1 minus of e raised to minus of h dl divided by m. So if it says that effectiveness of 1 is equal to effectiveness of 2, that implies that pi dl h pi dl of 1 is equal to h pi dl of 2. So here pi can cancel since a laminar flow h is dependent upon the Nusselt number, so you can write h is equal to nuk divided by day d dl1 divided by uh, NUK d by dl of 2. dd gets cancelled, k gets cancelled. Nusselt number is a constant that is equal to that is a constant wall temperature, so the wall is equal to the 3.66. That remains a constant for both the sides, gets cancelled. That means that this gives that for the same effectiveness, L1 is equal to L2. So it is independent of the length of the it is independent of the length of the tube. So for a constant wall temperature case, what you could say is that uh, and with the same effectiveness, that is, a final temperature will be the same. But if you reduce the diameter of the tube by half, what will be the change in the length? So basically, this analysis says that for the same effectiveness, even though we reduce the tube diameter by half, it is not going to affect the length of it. The same length can provide the same effectiveness. That's what this analysis of constant wall temperature says. Now we can look into the fifth problem. So water is heated as it flows through a stack of parallel metallic blades. The blade-to-blade spacing is d is equal to 1 centimeter, and the mean velocity through each channel is u is equal to 3.2 centimeter per second. Each blade is heated electrically so that two sides of the blade together release 1600 watt per meter square into the water. Assuming that the water properties can be evaluated at 50 degrees Celsius and that the flow is thermally developed, uh, fully developed, we can say we should verify the flow is laminar, calculate the mean temperature difference between the blade and the water stream, calculate the rate of temperature increase along the channel, show how long the channel must be so that the assumption that flow is fully thermally developed is valid. look into the problem. I'll also try to solve it within a minute. So, So first of all, we have to verify the flow is laminar and then calculate the mean temperature the difference between the blade and the water stream. It's a stack of parallel metallic blades. The blade to blade spacing is d equal to 1 centimeter. The mean velocity through the channel is 3.2. Each blade is electrically heated so that the two sides of the blade together release the total heat transfer to the total heat flux towards the fluid water is 1600 watt per meter squared. We have to calculate the rate of temperature along the channel and how long the channel must be so that the assumption that the flow is fully thermally developed is valid. So first of all, we have to, for the case of water at 50 degrees Celsius, we have to calculate K. K is 0.64 watt per meter Kelvin. Rho is equal to 0.988 gram per centimeter cube. Specific viscosity is 0.00554 centimeter squared per second, and Cp is 4.18 kilojoule per kilogram Kelvin. First of all, we have to calculate the Reynolds number. It's a parallel plate, so hydraulic diameter is 2 times the thickness between the plates. So the hydraulic diameter is 2 times T is equal to 2 centimeter. The Reynolds number with respect to the hydraulic diameter is U hydraulic diameter divided by nu. U is 3.2 centimeter per second, 2 centimeter divided by 0.00554. So the value is 1155. So it's a laminar flow. Is equal to H into hydraulic diameter divided by K. It's a flow between two parallel plates. Uh, Metallic plates, and it's a fully developed condition. So with respect to the hydraulic diameter, we could write the Nusselt number is equal to 4.364 is equal to HD hydraulic divided by K. That is equal to, from this, H is equal to 4.364 into K is 0.64 divided by hydraulic diameter is 0.2 centimeters, 0.02, that is equal to 140 watt per meter squared Kelvin. So in this process, we need to determine the value of the mean temperature difference between the blade and the water stream. So we know that the heat flux is equal to H into T wall minus of T mean temperature. Therefore, from this, you can get the T wall minus T mean is equal to heat flux divided by H. So the heat flux is 1600 watt per meter squared per a single blade. 1600 watt per meter squared for both the blades combined together. So 1600 multiplied by the 2 times area will give the total heat transfer. So uh, per single volt, the heat flux could be written as if you assume the wall temperature to be TW and Tm to be the mean temperature from a single side, it will be equal to from a single blade, it will be equal to half the heat flux. So watt per meter squared. It's been mentioned that the two sides of the blade releases 1600 watt per meter squared as a total area. Taking the cross-sectional area, we'll get 1600 into area will be the total heat transfer on both the sides of the blades. So flow happens between two blades like this, and similarly the same extends in these directions as well. So the total heat transfer is 1600 watt per meter squared by the blade. So the two surfaces, the two areas uh, will be active. So taking a cross-sectional, constant cross-sectional area, uh, so the amount of heat that happens that flows towards a fluid from one side will be equal to 800 watt per meter squared for the same cross-sectional area. And similarly, 800 flows through 800 is transferred to the fluid from the top as well. So what you could say is that per blade it is 800 watt per meter squared, 800 watt per meter squared divided by H. H is 140. Both the sides of the blade are active. That's why the total heat transfer is 1600 per the cross-sectional area of the blade. That is in contact with the in contact with the water. So that's how we have written So 1600 minus the area divided by 2 will be the heat transfer from the blade to the fluid. So this can be a slightly tricky problem because if you assume that both the sides of the area, both the sides of the blade are included in the heat flux, then the 1600 itself will be, in terms of the heat flux, 1600 watt per meter squared itself will be transferred from the blade to the fluid. So depending upon that two values, the actual value might change. So the value of TW minus TM, wall temperature minus mean temperature, will be equal to 5.73 degrees Celsius. Now we need to determine, so this is the wall temperature difference. So in the problem, it is been asked to calculate whether the flow is laminar. We have assumed, we have found out that flow is laminar, and then we have calculate the mean temperature difference between the blade and the water stream. Yes, this is the mean temperature difference between the blade and the water stream. Now we have to calculate the rate of temperature increase along the length. So this is section 3. So we have to calculate dTm divided by dx across the length. So this is equal to, this can be obtained from the energy balance of the fluid that flows between the two blade streams. So that is equal to heat flux divided by rho Cp into U rho Cp into U into cross-sectional area into length. So that will be equal to the mass flow rate term, rho into velocity area into velocity. Sorry, this is U, rho into Cp into area cross section. So Q double dash multiplied by the area surface. Sorry, perimeter surface multiplied by dx will be giving you the area of the surface area. So the heat flux Q double dash into perimeter into dx will be equal to the change in temperature multiplied by the enthalpy change of the fluid that flows between. So rho Cp U into area of. So in this one, we can get this is a blade thing. So the distance between the two blades is given. The heat flux is given as 800 from one side. So if you assume the heat flux from one side is Q double dash. So taking the mean temperature and the wall temperature on the one side, you can get the heat flux. So it's basically 800 into perimeter will be equal to the 2 times of the width. The other dimension is very small, divided by rho Cp into rho is 0.988 gram per centimeter cube. Cp is 4.18 joule per gram Kelvin. U is the mean velocity 3.2 centimeter per second. That is given in the problem. Mean velocity is 3.2. And then in the last term, the cross-sectional area. So that is equal to the width into the D term. So W gets cancelled, only D remains. That is the width across. So the dou T by dou X is equal to 1.21 degrees Celsius divided by meter. So solving these all parameters, we get as the temperature variation. The temperature rate of temperature increase along the length is 1.21 degrees Celsius per meter. So the last section of the problem, we have to show how long the channel must be so that the assumption that the flow is fully thermally developed is valid. So for that, we need to calculate the entrance length. For the flow to be considered fully thermally developed, the entrance length parameter needs to be considered. So for that, we use the equation that we have formulated in the previous week. the entrance length, the thermal entrance length, XT is of the order of 0.1 into hydraulic diameter with respect to the Reynolds number with respect to hydraulic diameter, Prandtl number, and the hydraulic diameter. So that will be equal to 0.1 into 1155 into Prandtl number for water is 3.57, and at this temperature, and hydraulic diameter is 2 centimeters. So that will give the value of 8.2 meters. So that is the entrance length. Therefore, the length of the tube must be very much greater than 8.2 for the assumption of thermally fully developed assumption of thermally fully developed to be satisfied. Fully developed to be satisfied. So that solves this problem where this is slightly confusing as such, where we have taken the heat flux. So 1600 watt per meter squared is released from both the sides of the blade. So if you assume a constant area of the blade, then the from one side 800 watt per meter squared will be delivered to the water, and based on that we have calculated. So if you assume it to be 1600, the actual values might differ as well. Look into the last problem. It's a multiple choice question. In a fully developed laminar flow at uniform wall heat flux, variation of temperature with axial distance at a fixed radial location is parabolic, linear, quadratic, exponential. So this is something that we have seen. It's actually linear. So how it happens is that we know the temperature. From the lectures that temperature at a axial distance and a radial distance x comma r could be written as the wall temperature T wall of a particular x minus of the heat transfer heat flux multiplied by the heat transfer coefficient into the temperature profile with that is depending upon the dimensionless variable. So this means that dou T by dou x is equal to dou T wall divided by dou x, because this is a constant at one particular r value, keeping an r constant for a constant r for some particular value, dou T by dou x will be same as that of dou T w divided by x. So we assume that r is a constant in this case at a fixed radial location given in the problem. So dou T by dou x is equal to dou T w divided by dou x. Also from the heat flux equation, what we could write is as q double dash the HLC, the heat transfer coefficient. So this is equal to q double dash d divided by k divided by the wall temperature minus mean temperature at a particular x is of the order of 1. So that's why we have seen the Nusselt number for a for constant heat flux case for a parallel for a supply tube is 4.36, for parallel blades it's somewhere around 8.2. So in this case, could see that based on this, we could see when we differentiate it with respect to x, we could see that dou t 0 by dou x is equal to dou t m by dou x. So one equation says that this, and the second equation says this, and therefore what we could see is that dou t by dou x is same as that of dou t m by dou x. So this dou T m by dou x is nothing that we have seen in this previous case. Dou T m by dou x is equal to Q double dash into the perimeter divided by rho CPU AC. For the case of circular tube, AC cross-section area is pi by 4d squared and the perimeter is pi d. So we'll get it in terms of 4 times 4 by d, that is equal to 2 by r. So that will be equal to 2 by r outer into Q double dash divided by rho CTU. So what this is a constant, R outer is a constant, heat flux is a constant, as given in the problem, rho is a constant, Cp is a constant, and an average velocity is constant. This means that dou Tm by dou x is a constant. So the variation of temperature with respect to x shows a constant the slope for all the things. So if this is constant heat higher wall temperature, the mean heat flux will be having the same slope as that of the wall temperature, and the slope of the temperature at any profile will also follow the same as that of these two slopes. So the slope will be linear. So what we could see is that variation of temperature with axial distance is linear. That's the slope is a from the slope it is linear. We could say that it's a line. Variation of the temperature with respect to x is a linear. Note it doesn't form any other. It doesn't have any other dependencies. That solves the problem solving session for this week. So in this case, we have seen few derivatives based on the hydrodynamically fully developed case to calculate the average shear stress and the friction factor, and to calculate the Nusselt number for uniform wall heat flux case. We couldn't see much into uniform wall temperature because that requires an iterative process, iterative solver to solve it. We can't directly get the values as such. And we have seen a few multiple choice questions based on this heat flux, and we have seen several variants of it. 3 multiple choice questions, and finally we have seen a few numerical type questions and few multiple choice questions as well, and a single multiple choice question that deals with the uniform wall heat flux case. So if there is any confusion, you can post that in the forum. Yes, I understand that there is some kind of a confusion in this problem, so I can look into it and I can clarify once someone posts in the forum. That's all for this session. We'll meet next week with the next week lectures. Thank you.